All right, let's talk about bond theory, which, yeah, is as cool as it sounds. So, in particular, valence bond theory, this is really what we've been talking about. So, valence electrons, those electrons in the outer row. What valence bond theory essentially says is that atoms share their outermost electrons in order to achieve an octet. So, an element that has 7 valence electrons is going to share, so it gains one more and gets its full octet. And so really what it says is if you have a nucleus of one atom and a nucleus of the other, when those two bond, what's happening is their valence bond electron shells are overlapping. And so right there would be where the sharing takes place. So let's take a look at how this would take place, tying it in with the orbital notation from electron configurations. So this is where orbital theory or orbital notations come in really handy because what we know about valence bond theory actually kind of matches with electron configurations. So we see that boron, which will form boron trifluoride, so it'll bond with 3 fluorines. Remember that boron only needs 6 valence electrons. Right here's its full orbital shell, 2 in the 2s, 1 in the 2p, and then fluorine, of course, only has 1 empty spot in its 2p shell. So when boron shares electrons with fluorine, it means that this one and that one are going to be shared between boron and fluorine. And so really we can say that this electron right here would come over and be right there being shared with that guy. But there's 2 more fluorines. So where does it share its electrons at? So here's our other 2 fluorines. Each one has its lone electron that's looking to share. So if they come here and they share in this box, let's say, so that we'd have an up and a down in there, well, if both this fluorine and this fluorine are sharing electrons in that orbital right there, that sublevel, then is fluorine really sharing with boron? No, since they're occupying a room together right there, that means this fluorine is sharing with that fluorine, not with the boron. This fluorine is because its electron is right there with boron's, but these two are sharing with each other. So that doesn't make sense. And when something doesn't make sense in science, what do? Yeah, we just forget about it and move on, right? No, we look for a new theory to make sense of what doesn't match up with our current theories. So here's what we think happens. Instead, boron is going to excite one of its electrons, so it's going to take its 2s electron and bump it up into the 2p. Now what happens is we have 1, 2, 3 places for boron to share electrons. That means that 3 fluorines can come in here and they can put their electrons in with borons, bond in 3 different places, and give us BF3. So 1 boron is going to be sharing in the S sublevel, and then 2 of the fluorines are going to be sharing in the P sublevel. So whoa, here's how that would look. And let's try and make sense of this. So remember, S and P, S is a circular shape. So right here, there's the 2S of the boron, and then P's kind of make a dumbbell shape, so really you can't see it back there, but this and this P right there are attached to each other, and they're making kind of that dumbbell shape like that. It's just hidden behind the 2S. And then PY, that would be also behind the 2S, and so that it makes its own little dumbbell shape. So then there's 3 fluorines. Remember this fluorine right here? That's the one that's sharing the electron in the 2s shell. And that fluorine is sharing in the 2py, and that one's sharing in the 2px. So that just goes back to the last slide where those 3 fluorines were sharing. Here they are sharing. However, BF3, 3 electron domains because there's no lone pairs in boron. So what shape would that be? It would be trigonal planar. And we know that the ideal bond angle of trigonal planar is 120 degrees. If we look at this picture right here, though, px, py, that means x and y axis, so that's flat, and it makes a 90-degree grid. So according to that, the bond angle between these guys would be 90 degrees. There's a 90-degree bond angle between those fluorines right there. That doesn't make sense either. So we just forget about it and move on, right? No! New theory! So the problems with the valence bond theory is it says that 90-degree and other random angles for fluorine bonded to the s orbital. Vesper says that it should be 120. So they came up with something new called the hybrid orbital. Yeah, the hybrid orbital. So when an electron is promoted from s to the two p's, orbitals are going to morph into three separate but identical hybrid orbitals. So instead of having one s and then two p's where it's sharing, instead all three are going to be sharing in what's called an sp2 hybrid orbital. And here is what that would look like. So boron would be right here. That would be its nucleus somewhere in there. And then you'd have this sp2 hybrid orbitals where it is sharing. So when we have three identical guys making this new shape, as a result, we get 120 degrees, like we should. So this matches Vesper. So the 2s and the two 2p's meld together to make this new hybrid orbital. It's kind of like a liger. When you mix a lion and a tiger, you get the best of both worlds and a whole new shape as a result. So let's look at it mathematically then. We have our s orbital right there, so that would be 2s in the case of boron, and then we have our py and our px. Now instead of them staying as separate identities, when they come to bonding, they're going to form into these sp2 orbitals. And so you can see it's kind of a joining of the p's and the s's. You've got a little piece of the s, a little piece of the p, and three new places to bond. But the fun doesn't stop with sp2. There's all kinds of hybrid orbitals. Let's take a look at methane, which is CH4. So if we look at carbon, according to its orbital notation, it really only has two places that it can share electrons. It doesn't want to share any in there, because if it did that, they would just be sharing with themselves, not with carbon. So what does it do? It's going to promote one of its electrons from the 2s up to this empty 2p. And now it has this orbital notation, which means that we have one spot in the 2s and then three spots in the 2p. And they're not going to stay separate, though. It's not going to stay its own 2s and then those three 2p's that are separate. Instead, they're going to morph together, and they're going to create a new hybrid orbital composed of 1s plus 3 p's. And so what do we call it? We call it the sp3 hybrid orbital, because it's made of 1s and 3 p's. And what we've created now is 4 places for carbon to share bonds with. So now this hydrogen right here that has one valence electron, it can share. We can take 4 different carbons, and we can share in these 4 different places. And so here, this is what this would look like. So the sp3, which would have bond angles of 109.5, it's a conglomeration of an s and 3 p's, gives us this three-dimensional, four-sided shape called a tetrahedral structure. So let's build water with the valence bond theory. So valence bond theory, that's the first one, the one that doesn't quite work. Remember, where they're just sharing on the outside, overlapping thing. So if we share hydrogens with oxygen, well, it looks like it makes sense. So it goes right there, goes right there. It has those 2 empty spots on oxygen, gives us some H2O. But if you look at how this would actually lay out, since oxygen has P, X, Y, and Z, that's like a 3-dimensional grid with 90 degrees between all of the axes, when those hydrogens came in and bonded with the Y and the Z right there, you're going to form 90-degree angles. But Vesper predicts that it won't be 90-degree angles. It should be 104.5. So this doesn't make sense with the valence bond theory. But that's okay, because we have the orbital theory. So here's just what we were saying before, why it doesn't make sense for water to use the valence bond theory. So instead, it creates an sp3 hybridized orbital, not to create more room for electrons. Okay, there's always room to share electrons with the oxygen, or had 2 places already, but instead it was to relieve the strain. With the hybrid orbital theory, it forms 104.5 degree angles, which is a lot less sharp than 90-degree angles, so it's going to be a lot less strain on the atom itself. Remember, molecules are lazy. They want to have as little energy expelled as possible, and if it means relieving their strain by doing a hybridized orbital, makes sense for them, makes sense for us. So, but in this case, the 2s is not promoted up to the 2p. Instead, all three of them just come together, all four of them come together to make these four sp3 hybridized orbitals. And so the sharing is actually happening just in those two right there. These ones right there, 2 electrons, both on oxygen, these would be lone pairs. So lone pairs too can take place in the hybrid fun. So here we see it with a nice pretty 104.5 bond angle, bent structure. We have our bonded hydrogens right there with strain relieved. Up there we have our other sp3, and those would be our lone pairs chilling up there. All right, the take-home message then for hybridization, you're going to need to be able to figure out what type of hybridization takes place for a particular structure. So you draw a Lewis structure. You figure out what its VSEPR structure is. You figure out what the hybridization is. The way to do it is count your charged clouds. So something that has 2 charged clouds, that could be bonds, it could be electrons, lone pairs, would be sp hybridization. Something with 3 charged clouds would be sp2. Something with 4 charged clouds would be sp3. Good way to remember this is just look at this number. So if there's 4 things, S plus 3 would be 4. So we've got a 1 plus 3 is 4. 1 plus 2 is 3. There's 3 right there. And then 1 plus 1 would be 2.